So the issues I'll be focusing on today in surface water treatment include disinfection byproduct formation. Both THMs and HAA5s tend to fall under that. Sprinkled within these discussions, I'll also be talking about operation expense optimization. This can be done in a variety of ways, improving enhanced coagulation to reduce coagulant usage, as well as just simply being a cheaper chemical to generate. And then finally, we'll also touch on ammonia removal. And if you've seen the previous presentation, we went into ammonia removal in fairly good depth at groundwater. But ammonia is actually an issue on surface waters as well, largely due to farm runoff. So our fertilizer from farm runoff can get into surface water sources and prevent some real challenges for municipal water treatment plants. So disinfection byproduct formation reduction. There's a couple ways in which we can help with this, and this is actually one of the chemistries where mixed oxidants really has a nice fit. So if you are suffering from elevated THMs or from elevated HAA5s in either before the distribution system or in the distribution system, mixed oxidants might be a really nice fit to take a look at. Now, the problem can actually come in a couple of different places, and so how we fit into that will vary just a little bit depending on how you might do a little bit of troubleshooting. And so this is the way I kind of take a look at these types of applications and the way our team looks at these applications. So let's just say you have a typical surface water treatment plant, so you've got a surface source here, maybe it's a lake or a river. You'll go into some sort of a clarification and coagulation process. So it might be a traditional flash mix, rapid mix, followed by flocculation and clarification. This might be a solids contact reactor clarifier. It might be something like a cone-style system, like a claricone. After that, the settled water will typically go to granular media filtration of some kind. Alternatively, you might be looking at something like ultrafiltration at that point. There are a number of systems out there that have a pre-treatment prior to microfiltration. Then to a clear well, and this is normally where you're doing a couple of things. One, you are maybe adjusting your pH to give you a nice pH out in the distribution system that's unlikely to corrode. If you're, you might be looking to stabilize it in some other fashion, but most importantly, you're usually adding chlorine prior to the clear well, or this might be a storage tank in order to give you some contact time to achieve your ideal disinfection time and concentration, also known as CT, either by regulatory or performance-wise, and you'll go ahead and put that through there and then out to the distribution system. And so we kind of like this, so we say that's upstream, and then after the clear well you may have some high service pumps or maybe just piping from elevated storage, and that will go out to the distribution and that will go out to the homes. So what I like to say is this juncture right here, where it be post-clear well and prior to the distribution system, is really a critical point to take a look at. So if high disinfection byproducts are being measured prior to the distribution system, so if you're having problems even before you get out to the distribution system, improvements in pre-treatment are really what you need to focus on, and where mixed oxidants can come into play in this case as well. If your DBPs are forming in the distribution system, so let's say you're fine after the clear well, you have low organic content, you have low disinfection byproducts, but you're seeing that the disinfection byproducts are forming in the distribution system and are significantly increasing the distribution system, then it's another opportunity to perhaps consider mixed oxidants. A lot of times that this can indicate that there's biofilm in the distribution system that we can help remove and help improve your performance. So a little bit different graphical way of looking at this. So again, we have a typical water treatment plant layout. Obviously, this can look a lot different in a lot of different ways, but we would be looking at, depending on where your problems are, and we always like to go to our customers or our partners when this question comes up and ask for some detailed information. You like to ask, what does your water treatment plant process look like? When you say, I have a problem with THMs, what exactly do you mean by that? Where are the THMs a problem? How high are they? How far out of compliance are you? We like to get that kind of data, detailed water quality analysis, to sort of help work through where we might be able to help out. And usually we'll be looking at either adding mixed oxidants prior to the water treatment plant process, so just prior to flash mix flocculation, to help enhance the coagulation process and get better performance in TOC or DOC removal in the water treatment train, or prior to the distribution system if there is reason to suspect that the distribution system is actually part of the cause of your problem. So we'll take a look at the upstream first just a little bit. A lot of times you may hear of us talk about the microflocculation effect and what that actually is. And really in its simplest form is it's actually doing something that maybe is a bit counterintuitive. So some of our customers may say, oh my gosh, why would you put a chlorine-based product prior to my settling basin if my problem is disinfection byproduct formation? Because won't me adding chlorine further up the stream actually create more problems? And in reality, the microflocculation effect, if it occurs, and we can do some things to predict whether or not it's likely to occur in your water, can actually help that. So it does feel a little counterintuitive, but can actually be a very powerful tool that you can use. So what the microflocculation effect actually is you dose a small amount of mixed oxidants prior to the addition of your coagulant, and it changes in a sense, the nature of the organic constituents so that they're easier to coagulate out and do two things. Typically, you're going to lower your chemical requirement for your coagulant, as well as improve your TOC and your turbidity that you're going to get off of your clarifiers. So graphically, you can kind of think about this. So when we're actually doing this, I should say, back up just a second. What we'll normally do is look at a water analysis, and we want to look at things like alkalinity, turbidity, and the relationships of those things to each other. And it can be fairly accurately predicted as to whether or not that microflocculation effect will actually occur. And so we can take a look at that and then give you an idea of whether or not it's worth investigating further. And if it is, it's very easy to do a series of jar tests in your lab. Most water treatment plants are set up, especially surface water treatment plants, are set up to be able to handle jar testing. So we can set up a protocol for you, and this is kind of how it would look. So this graphically represents, these two graphics here graphically represents what this would actually look like. So if at the top, let's say, is your control, so this is your normal chemical regime, and you may have alum dose, let's say optimal here is the number 4 on this first one, so you may have 5 different jars numbered 1 through 4, where you have an optimal dose is in jar 4, and then 5 is overdosing, and then 3 and below is progressively underdosing. And then you are comparing that along with moss. And so what you'll do is typically you will go into these jars, you'll put a very small amount of mixed oxidant solution. Usually you're only looking at a couple tenths of part per million, maybe a little bit more. Dose all of those, and then dose a very similar regime as the top level. So the bottom level, you'll have the moss pre-feed, and you'll compare that to your control up above. And what you'll typically see is that optimum level will shift. So instead of, let's say, 4 was at 20 parts per million and 3 was at 15 parts per million, you'll typically see that the moss solution, you may see 15 parts per million as your new dosing regime, just by dosing a small amount of mixed oxidants prior to it. Then the second thing that you can typically do if you want to go one step further off of this is you can actually take that supernatant, filter through some filter paper, and actually take a look at what the difference between your TOC or your DOC between your control and your test, either by using something like UV adsorption as a surrogate or a direct test itself. So this has a couple of big benefits. So first of all, if this effect occurs, and it actually occurs in a surprising amount of sources that we've looked at, it can do 2 things. First of all, it can greatly enhance your TOC and your DOC reduction, which means you have fewer organics with which to react with chlorine downstream and form disinfection byproducts. The second thing that it can do is reduce your coagulant usage. And it's not entirely unusual to see things like alum be reduced by 40%. And this just shows this is an example that we have where we using Rio Grande water for a plant at 8.2 mgd shows evidence that moss can be used for pre-oxidation reduction of alum. So a test was studied, And indeed, they did show that when comparing the turbidity on the y-axis here versus the dose, and comparing the blue graph, which is the coagulant versus only versus coagulant plus MOS, you can see in each one of these cases at a lower dosage, they got even better turbidity coming off of the clarifier. So what does that translate into? Well, not only do you have potentially the advantage of lowering your TOC and your disinfection byproduct precursor formation, but you also have an opportunity to save a lot of money. So if you are looking at converting regular bleach or chlorine, for example, over, and the mixed oxidant does do this, does get that effect, and even just assuming a 30% reduction in alum and polymer, you can see that for a 7.5 mgd plant, starting at about almost 30 parts per million dosage and about half a part of polymer dosage, you can actually see that this will pay itself off in approximately 1 year. So not only do you get an enhanced advantage, but you also get significant savings and the ability to see a very, very short return on investment. So now, if disinfection byproducts are forming in the distribution system, that may indicate the presence of biofilm. And so one of the, again, sort of as we start looking at this, we like to look at what are the behaviors and what are some of the disinfection byproduct concentrations that you're observing. So a great example is if you are putting, let's say, a couple parts per million in just prior to the distribution system or just prior to the clear well, and then you start looking at your sampling points in your distribution system, and really almost a ideal indicator that this is a potential issue is if let's say your sample point close to the plant sees a concentration of 1.8 part per million, and the further and further away you get away from the plant, you see a continuous reduction in that chlorine to maybe even like 0.2 or 0.3 parts per million out at the end of your distribution system, and at the same time you're seeing disinfection byproduct formation occurring, that's a really good indication that biofilm exists in your system, and it is actually acting as two things. It's acting as a source of chlorine demand, as well as an additional carbon source for producing additional disinfection byproducts. So if you see those types of things in your system and you're struggling with disinfection byproduct formation, it's a really good indication that you may have a biofilm problem in your system. And in that case, mixed oxidant is an ideal solution to just simply replace your chlorine usage, switch it out with mixed oxidant, and clean that system up and improve your disinfection byproduct formation. So as I mentioned earlier, mixed oxidants help remove biofilm. They do a wonderful job of removing biofilm in not just drinking water applications, but pools and spas. In fact, the diagram on the left-hand side here is from a really dramatic borescope image of a spa in Japan that some folks, unfortunately, died as a result of exposure to Legionella. And once they made the conversion, and you can see the borescope images before MIOX that has biofilm on the recirculation loop in that spa of as much as 1/4 of an inch or more, and then after 22 days, the pipes are virtually spotless. And they saw that this material was beginning to slough off almost immediately after starting to dose the mixed oxidant solution. Some other interesting observed effects are, one, prior to the conversion, they were seeing greater than 5 colony-forming units of Legionella. Afterwards, no hits. And they were having to dose 1.5 part per million to maintain a residual of 0.2 parts per million. And after it, they were able to dose just 0.6 parts per million as free available chlorine to maintain a residual of 0.4. So again, this is a great microcosm example of how biofilm can create a significant chlorine demand, and how getting that out of there and cleaning that out of there can greatly reduce the amount that's required. Moving to a city in Texas that will leave nameless, that had converted over to mixed oxidant. Just in case you're actually drinking the water, we don't want to make people feel unpleasant. There was a city that was using gas chlorine in Texas and had noticed in their distribution system prior to the conversion, when they would have to maintain some of the pipes, that there was a brown, slimy film that was noticed quite commonly in pipes, in particularly certain legs of the system. So they made the decision to go ahead and make a conversion, and 1 year after MIOX, while maintaining another section of pipe, you can see that even though the pipe on the left-hand side is much further away from the plant, and the plant on the left-hand side, it's 1/2 mile versus 200 foot from the plant, that pipe is now clean and has remained so when they've had to do other maintenance since. So it has done a wonderful job of removing the biofilm. And one of the things I would like to it's probably worth mentioning is this effect of cleaning out and reducing the demand as well as the carbon source actually is a twofold effect. So not only do you reduce the demand and then don't have as much additional carbon source, but by reducing the demand, that means you have to put in less chlorine into or just prior to the beginning of the distribution system, which means that your initial concentration is lower. And as I think most of you realize, disinfection byproduct formation is really a combination of three things: the concentration of your organic precursors, the concentration of the chlorine, and the time involved. So if you can reduce any one of those things, you reduce either as I mentioned, the concentration of the precursors. If you can reduce the chlorine concentration, you normally don't have a lot of control over time. So the two things you have to focus on are those two things. And by cleaning up the biofilm, you certainly address the chlorine aspect of it, as well as the carbon precursor aspect of it. We have a lot of examples out there where this has occurred. This is just one for Cotaloro, Puerto Rico, where they tracked the disinfection byproducts over time before and after. And on average, we were able to reduce the disinfection byproducts after the system was put online by up to 35%. And this is actually a really interesting graph, I think, because the system was put online right at Q2. So you can see that when the system was put online initially, just right away, the disinfection byproducts with the mixed oxidant were actually very close to that of chlorine gas. So right as the system goes online and it hasn't had a chance to really do its work yet, and there's still biofilm in the system, it's pretty darn close. Then over time, you can see that as that system begins to clean up, the disinfection byproduct concentration with mixed oxidant continues to drop, whereas even the chlorine gas concentration, as compared to the previous year, was peaking in the Q4 comparison here. So you can see that over time, as the system has a chance to work, it can drop significantly. And in this case, they saw a drop year on year on average of 35%, but seasonally even greater than that. So we'll kind of move on to ammonia removal now, and as I mentioned, if you've sat in the other ones, we have spoken about this a little bit previously, but this is it depends a little bit on where you're located. So there are a lot of plants out there that struggle with ammonia in a surface water source. Typically, the bad actor in this case is fertilizer runoff, either from agricultural usage, or in some cases it may even be from home use. So people putting fertilizer on their lawns, over-fertilizing, and having runoff out into the receiving streams. And then this can get into, if there isn't a large body of water that has a long time to biologically reduce the ammonia in the water body prior to the water treatment plant, this can be brought into the water treatment plant and has to be dealt with. So it can be accomplished in a variety of ways. One, you can remove that with biologically active filters, although that's not very common in drinking water systems. It's kind of, again, it's one of those things that sounds a little counterintuitive. You're a drinking water system, you're supposed to be very, very clean. A lot of people don't naturally think about purposely growing bacteria on their filters in a drinking water plant in order to address a problem. So it can be a bit of a public relations challenge. It can also be very difficult to control, especially if the ammonia is seasonal. I know that in the Midwest here, where in my former career, I have actually done a couple of these projects. We would run into some real issues in the winter when the temperature would drop significantly and there wasn't a significant food source, and it was very difficult to keep those bacteria alive and active until the next year. And so some plants actually have to dose things like methanol as a food source in order to keep those organisms alive. And so that can be very, very challenging and expensive to do. Nanofiltration or reverse osmosis can be used. Operating costs can be very high. Normally you're looking in dollars per 1,000 gallons, or I should say at least the high tens of dollars per 1,000 gallons produced, which is very expensive for a municipal water treatment plant. Also, disposal of the concentrate stream can be a challenge. So most of you that are familiar with this know that you create a high ionic strength waste stream with either one of these two processes, and in many cases the wastewater treatment plant can't take that as a waste product, and so something else needs to be done with it in order to dispose of that waste product. Finally, you can also breakpoint chlorinate to convert the ammonia to nitrogen, and this can require a very high volume of chlorine and can be a challenge to control. And I'll talk about that just a little bit and how we can assist with that as well. But all of these are actually challenging ways of dealing with ammonia. I would have to say of the three methods, the three most common methods that are listed here, breakpoint chlorination is probably the simplest because it's just addition of some additional chemistry. You don't have any other mechanical equipment to deal with, and so it can be a very, very simple way of handling what can be a challenging problem. Also has the ability to deal with varying concentrations quite readily. So in the winter when you may not have as much, or seasonally when you may not have as much, you just don't dose as much chlorine. And it's very, very easy to do. So I get this question a lot about, well, how does breakpoint chemistry work? I don't understand breakpoint chemistry very much, and that's okay. That's everybody on this phone call can admit that if they don't understand it, they don't have to be ashamed. It is very complicated chemistry. There are a lot of reaction paths that can occur with ammonia to get to the final state down here at the bottom of producing nitrogen gas and chlorine. So this just shows some of the potential intermediate states that one could argue chemically that are actually occurring. So you can take a look at all of these different steps, and a chemist can make a strong argument for a number of these reaction paths and any one of these reaction paths and combinations going simultaneously. And in fact, this is an interesting graph that I'm certainly not going to go over in any level of excruciating detail. But Jaffert and Valentine in 1992 came up with this potential reaction chain or reaction scheme for the chlorination of ammonia-containing water. And if you're starting right here in the middle, they're arguing you can go any one of these various branches and argue that all of those are likely reaction paths that that the chemistry would actually take. So it is a very complex chemistry. And what this normally means is, if you can, and I guess a way that one of our, Dr. Wes Bradford, if you know him, he's one of our PhDs here in our R&D department. One of his things that he's fond of saying is, if it looks complicated, it usually means you have to dose a lot more than you were planning. So and I think in almost no example is that more true than it is in this case, in the case of ammonia. So if you condense down the simplest paths, this is what you can actually argue. You can actually argue right here that a couple of ammonias plus chlorine liberates nitrogen gas plus some chloride ions and hydrogen. And if you work out that chemical ratio, you would say that for every part of ammonia that you have, you need to dose 7.6 parts per million of chlorine in order to achieve that reaction. Now, why is that important? That means that is the absolute minimum of chlorine that you would have to dose in order to drive that reaction all the way through. And in reality, if you're familiar with drinking water treatment, you've probably heard ranges more in the range of 15, maybe even 17 parts per million in order to achieve that reaction. And that gets right back to the complexity of the reaction. So you may not drive every one of those reactions down this nice, easy path right away. You may actually be consuming a lot of chlorine, driving the reactions in some other directions, and then finally getting to this endpoint. So bleach very commonly, and again in my previous career when I was designing these systems, I would oftentimes recommend folks, you're going to have to plan on about 15 parts per million of chlorine bleach. Where mixed oxidants can fit into this is that we tend to drive the reaction much more closely to stoichiometric. So when we're recommending a design, we'll actually say you're probably going to want to dose somewhere in the range of 8 to 10 parts per million, which can save a significant amount of money on operating costs. I mean, you're just for the oxidation of ammonia alone, you're cutting 30% or more out of the potential cost of generating that solution or dosing that solution. As I mentioned, I often see high reports of high dosages and chlorine chemistry required. You'll see numbers all over the place in the literature. 15 to 20 parts per million is pretty typical, where you'll see those numbers end up for just regular chlorine usage. And also control of the system can be a little bit challenging. And another common question I get is, well, what is meant by breakpoint chlorination? And this is a nice graph that kind of shows this, and we can't take credit for this graph. This is from Gordon and others in '92 as well. And the way you can look at this is if across the x-axis you have the amount of chlorine that is being added into a water source. Now this is no scale, this is just to show behavior, versus the amount of measured chlorine residual. You'll see that if you have ammonia in the water, as the concentration begins to go up, or as you start to increase your dose of concentration, it'll appear that not much of it is reacting. So you may put in, let's say, 1 part per million, you measure a residual of 1 part per million. And you'll start to go up and up and up and up, and then finally you'll hit some point at which you start driving that reaction. So the ammonia will begin to convert. And at that point, let's say here we're at 2, we'll just call these hash marks 2, 1, 2, 3, 4. So at 2 parts per million, you'll measure, let's say, a 1.5 part per million, and then you'll start to come down over the curve. And then even though you're adding more and more chlorine in, so now 3, you're actually observing a lower level of, let's say, 1 here, until you get to sort of this inflection point down at the bottom when you know all of your ammonia has reacted and your concentration begins to come back up. And so this is where you've reacted all of your chlorine. So this beginning of this curve is you begin to react at this part of the curve. You start to really react, or I should say you're just prior to reacting at this upslope. You begin to react at the peak, and then you start converting your portions of your ammonia over. And then finally down at the bottom, you've gotten as good as you can get with your ammonia conversion. And then after that point, you start carrying the chlorine residual. And so the control of the system, if you're operating a system, and this is a challenge for you, you have to keep in mind that if you start dosing the system at, let's say, 1 part per million, you see 1 part per million, and you're still reading ammonia, it's because you haven't gotten past that break point yet. And this peak here is called the break point. So you haven't gotten past the break point, and you're not dosing them enough. So what this usually means is an operator has to pretty well know what's going on with their system. You know, what their ammonia concentrations typically look like seasonally, how much chlorine they have to add into the system, and so on. So when we're comparing, again, mixed oxidants, you could certainly do this with a bleach generator. So if for some reason you didn't want to buy a mixed oxidant generator and you really, really wanted to buy a bleach generator, you could. But what you would see is that a regular hypochlorite generator would need to be sized for approximately 15 parts per million per part per million of ammonia in order to achieve the effect. If you go to the mixed oxidant generator, you're really going to be sizing it based on 8 to 10 parts per million as free available chlorine per part per million of ammonia, which means you can put in a much smaller capital piece of equipment and your cost to operate will be much, much lower. And so if you do that comparison even against regular bleach or even just a regular hypochlorite generator, you're going to see that by reducing your chemical consumption by nearly 50%, you're going to reduce your chemical cost by nearly 50%. Plus, there's usually a delta between the cost to generate a mixed oxidant solution, it's usually about 50 cents a pound or so equivalent, versus $1.25 or higher, $1 or higher for delivered bleach on equivalent. And you can see that that becomes a very significant delta in operating cost between the two. And this just shows a typical ROI that you'd see for, in this case, it was a 2 MGD well source with 0.9 part per million of ammonia. And you can see the ROI crossover point here is at less than 2 years. So when comparing against regular bleach delivery, mixed oxidants can save you a lot of money in breakpoint chlorination from both the perspective of a reduced cost on a per pound basis, as well as reduced chemistry necessary to achieve the effect. So the summary of mixed oxidant breakpoint reaction, or MIOX experience with breakpoint reaction, the reaction tends to proceed at, near, or even in some cases a little below the stoichiometric requirement of free available chlorine to ammonia at 7.6. It's a very sharp contrast when compared with regular bleach. It's a much faster reaction. Reaction tends to be very fast as well, completed in approximately 20 minutes. Whereas reactions with bleach have been demonstrated to be slower. In actual treatment plant operations, this means that you're usually able to see the effect of it in the plant itself, as opposed to having to do further and further tests, or testing further and further downstream in your distribution system where the reaction continues to take place. And finally, if you go all the way through to breakpoint chlorination, the chlorinous odors can be greatly reduced. One thing that you also might be familiar with is incomplete reaction of the ammonia, or even reaction of ammonia with bleach, can produce that real swimming pool-y smell. We tend to drive that reaction further the completion, and so as a result, tend not to get a lot of the side product formation, and as a result, the chlorinous odors are greatly reduced as well.